we'll have Professor Chaitanya, who is an assistant professor in the chemistry department of the Indian Institute of Technology, Madras. And his research areas are in computational chemistry and material sciences. So today he will talk about using classical machine learning for improving some of the chemistry calculations, let's say.
Yes, thank you. Yeah.
Over to you.
Thank you. Thank you, Dina. So, is this slideshow visible?
Yeah.
Okay, cool. So, good morning, everyone. As Dina mentioned, so I am from the IIT Madras Chemistry Department. So, in this particular work, I will show you how we use the deep neural networks in order to predict the theta parameters of the wave function, and we perform the quantum chemistry calculations on quantum computers. So at the outset, I would like to thank Dina for giving me this opportunity, and I would also like to thank the students Kalpak and Sumit who have been working on these projects, and also the funding agencies, both the IIT Madras as well as the SERB. And I would also like to thank Professor Anil and the CPIC faculty. We have a center here, Quantum Computing Center at IIT Madras, and other group members for their support and encouragement, and IBM for the quantum computing resources. So in our group, we generally work in the areas of computational chemistry and material science, and we work on various kinds of problems such as simulating the charge transfer dynamics, catalysis, for example, water gas shift reaction or formation of ammonia in plasma atmosphere, etc. And we also look into the energy storage devices like anode materials as well as formation of the solid electrolyte interfaces. And also we are interested in understanding the degradation mechanisms of perfluoroalkyl substances. These are like water pollutants, and we study these kind of systems using both density functional theory as well as ab initio molecular dynamics. So recently we started working in the area of this quantum chemical applications using quantum computers. So we have started simulating various small molecules using the VQE algorithm, which most of you are aware of. So irrespective of whether we are dealing with a classical computer or a quantum computer, we will be either solving the time-independent Schrodinger equation or time-dependent Schrodinger equation. So if you are solving the time-independent Schrodinger equation, as the earlier speaker has mentioned, we will be considering a set of fixed nuclei and we will be optimizing the wave function. So these kind of methods are what we call as the electronic structure methods, where the nuclei will be fixed, but the electronic structure, that is the whole density, will be optimized. Whereas the second kind of set of methods are the nuclear dynamics methods, where you will be allowing both the nuclei as well as the electrons to move. So we tried to simulate both these kind of things on a quantum computer. So we were able to successfully simulate the Born of Oppenheimer molecular dynamics of an H2 molecule on a quantum computer. On the electronic structure side, that is predicting the ground states, we have done for various kinds of molecules. So I hope the audience already know the variational quantum eigensolver. So essentially, like, we are trying to predict the psi, which is dependent on these thetas. These thetas are the ones that are variationally minimized in this particular case. So once you minimize the thetas, so you will be obtaining a psi which will be minimizing the ground state energy. So essentially we are trying to find the best thetas that will give us the energy which is very close to that of the ground state energy, and that's the whole objective of the calculation. So considering this VQE algorithm, we have computed the energies, ground state energies, on a state vector using the variational quantum eigensolver, and these results are pretty well matching with that of the CCSD results. You can see the errors are in the order of milli Hartree to micro Hartree, so which is suggesting that these are very good results. But these are only on the state vector. When we went on to simulate the same kind of molecules on the real quantum hardware, we see that the errors are in the order of 0.1 Hartree or 0.01 Hartree, depending on the molecular size. Okay, so all these calculations were done using hardware efficient. So we tried to reduce the qubit and the gate counts. So once we did, for example, using when we reduced these ones, the errors are reducing. For example, if you consider only H2 and LIH, which I have shown in the earlier case, here you see that the errors are 0.02 and 0.37. that have reduced a bit when you are reducing the qubit requirement. However, when we go to the higher molecules, still the errors are in the order of a Hartree, which is obviously not very good. So this is the time where we came across a new article which has used the classical machine learning in order to improve the accuracies. So our aim is to get the accuracy as close to the chemical accuracy as possible, like less than 1 milli Hartree or so. So the new approach that we found is as following. So in this particular article, the authors have done normal VQE calculations. Let us consider for an H2 molecule at various bond distances. Once they did at various bond distances, for each bond distance, they have a set of theta parameters. That is the best wave function that they found. So using this thetas as well as the energies, they started to train the model, which is using the deep neural networks. And once they trained the model for any arbitrary distance, they were able to predict the proper thetas, and through which they were able to construct the potential energy surface. So you first train the thetas, finally you predict the thetas and the energies. That's all the whole scheme is. So they used this UCC, GSD and SAS, G corresponding to the generalized one, but they performed all these calculations only on the state vector. So what they suggested is this VQE and DNN-VQE, both of these results will be very similar is what they have shown, but they showed only for the case of state vector simulator. We thought that this is a good opportunity to check both whether it is going to work for the hardware or not. And additionally, if it works, we would like to go ahead and do it for the case of MD simulations, because during an MD simulation, there will be several bond distances at which you need to compute the ground state energy. So this was the motivation for which we did this particular work. So first we computed for the case of hydrogen molecule, the same kind of work that they did. That is essentially we repeated the work here with both 1 qubit, 2 qubit and 4 qubit results. Here are the data. As you can clearly see, their results and our results are matching very well, and our results are matching with respect to the FCI results also. Here VQE corresponds to the normal VQE calculation, where the initial set of theta parameters will be guessed, and there will be a continuous iterations that will be going on in order to find the final set of theta parameters. Whereas in the case of DNN-F, what we will be doing is we will be starting with the DNN, this deep neural network machine learning predicted parameters, and we will continue to run the VQE calculations. And in the last case, we will just take the DNN predicted parameters and we will perform only one iteration. So these are the three different kinds of calculations we did. All of these calculations are on state vector. So once we did, here I am showing the deviations. You can see that DNN1 is deviating slightly higher when compared to the others with respect to the FCI results, full configuration interaction results. But you can see that the errors are in the order of 10 to the power of -4 to 10 to the power of -6 Hartree. That means like already we are with good scale. So irrespective of whether I'm using DNN1, DNN-F or VQE, all of them are giving the results that are very close to the FCI results, which are at least useful for us for calculating the chemistry calculations. And also these results confirms that whatever the models that we have trained are working and they are as good as the earlier predicted values. So with the success of this H2 molecule, we went on to do the same kind of calculations with LIH. Here I am just showing the deviations with respect to the VQE. You can see here again that for DNN1, that is, I take the parameters predicted by the DNN the machine learning, and I will perform only one iteration. If I do so, the errors that I am getting are actually within, like again, more or less close to the chemical accuracy, 10 to the power of -4 order. So both of these results, both for the H2 and LIH, is suggesting that if I am using DNN, the results will be as good as that of the VQE. Furthermore, if I am performing DNN versus VQE results on a real hardware, what will happen is, like, this is not done on real hardware, these are still state vector results, but the number of iterations that you need to do in order to converge to the final theta parameters, if you compare, the red ones are the VQE, the blue ones are the DNN-VQE. You can clearly see that the number of iterations that you need for DNN-VQE are very low. Considering the amount of computational power that we need on a real hardware, you can clearly see that if you go with the DNN-VQE, the number of iterations will be less. That means the computational power that you require will be very less. So that means a faster convergence can be achieved if you are starting from DNN trained parameters instead of randomly starting from some random thetas. Okay. So till here the major conclusions are on a state vector, both DNN1 and DNN-F, both of them provide very good results that are close to the VQE accuracy. DNN1 has a huge potential for obtaining ground state energies on hardware because you are only performing one iteration there. Because we are doing one iteration, the errors will be very less that will be creeping in. And wherever you are going to use VQE, it is better and safe to use DNNF, because both of them, if you remember this plot, both of them are in the very close to each other. The errors are very less. So you can use either VQE or DNNF to get as close as the chemical accuracy as possible. But DNN1 also is good enough to get the results. So with these preliminary results and with the success of this, we thought we would go ahead and compute on the hardware these kind of calculations. So first we started with a noisy simulator for only 1 qubit hydrogen molecule. So we did the normal qubit tapering techniques like Z2 symmetries and parity mapping, etc., in order to obtain 1 qubit. Once we did that, we started to see already the deviation. So here you can see these are the VQE results, which are like way off from the FCN. Whereas for the case of DNN and DNNF, they are like coming close to 10 to the power of -2 order. Okay, and additionally, you can clearly see the difference between DNN1 and VQE results. Clearly, DNN1 or DNNF are order of magnitude better. They are predicting the results in an order of magnitude better than that of the VQE. Further, when we added this T-Rex error mitigation, then the results were becoming much better than the normal without the raw results. Okay, so as such, as the earlier speaker has shown, when compared to the raw results, if you are performing the error mitigation, the results are becoming better. For the case of H2 molecule, at least we are seeing that the errors are in the order of 10 to the power of -4 Hartree. That means these are good results to go ahead and perform the chemical calculations. Again, with this result, we went on and tried for the LIH. However, for the case of LIH, as you can clearly see here, the differences are actually very huge. They are on the order of 0.1 or more Hartree. So although we thought that DNN1 would give us the best results, we could not get that. So to understand why there is such a huge deviation, we went back to the H2 molecules example and we tried instead of 1 qubit with 2 qubits and 4 qubits. Okay, so this is like the 2 qubit circuit that we have considered. With the 2 qubit, if you are considering the results of DNN1, DNNF and VQE, again you can see that VQE results are very poor when compared to DNNF or DNN1, and here surprisingly DNN was giving better results than even the DNNF. And when you compare after the error correction, you can see that the results are in the order of 0.01 Hartree. Okay, so these are good, and the point that we wanted to make from this is VQE results are continuously worse when compared to DNN case of results, even when the circuit's depth is increasing and the number of qubits are increased. So we also performed the DNN1 level calculation, since as you can see here, DNN1 is giving better results. So we went on and we calculated the DNN1 results on the real hardware. Okay, that is IBM Brisbane we chose here. The earlier simulations that I showed are for the QASM simulator with noise model. So you can clearly see, even with the case of real hardware, when you apply the error mitigation schemes like T-Rex, the results are coming in the order of 10 to the 0.01 or so, okay, or even more than that. I mean, better than that also, 10 to the power of -2 to 10 to the power of -3. And between 1 qubit and 2 qubit, obviously 1 qubit results are far better than that of the 2 qubit results. Again, I'm just emphasizing these results are directly from the hardware. So again, here the point I wanted to mention is the DNN results are giving better accuracies than the VQE. So we went on and studied even for the 4 qubit case, where the depth has now increased to 97 qubits and the gates have increased to 190. In this case, when we performed already the error mitigation corrected ones, so you can clearly see that the errors still, even for the DNN and DNNF, are in the order of 0.1. So 0.1 Hartree or so. So what it suggests is, like, as we are moving, so the problem that we faced with the lithium hydride molecule is the errors are huge. So it is not about the molecule the errors are coming, rather it is majorly coming because of the circuit depth is increasing. And we could prove that by just increasing for the same H2 molecule, for which when we are considering the 1 qubit case, the errors are pretty minimal at 10 to the power of -4 order. But when we went to from 10 to the power of when we went from 1 qubit to 2 qubit or the 4 qubit, the errors started to increase. So essentially this is coming because of the increased depth of the circuit and the number of gates that we are using. So we also performed the hardware results on the for the H2 molecule with 4 qubits. Once again, we find that the errors are in the order of 0.1 Hartree, which are not acceptable for doing any chemical calculations. So as such, the point I wanted to make also is like we are not just alone like in getting this kind of errors. Whoever has shown like better accuracies, etc., they have majorly used only 2 qubits, and majority of the calculations that were reported in the literature are only for the state vector. And as we have shown in the beginning slides, for the state vector we are able to get very good results. But the moment we start even with the noise models, the results start to deviate very much, and they cannot be useful for the chemical accuracy. And we need to see what kind of new methods that we need to use in order to get to the chemical accuracy. So to conclude, circuit depth is one of the major causes for the poor performance. But if you simply try to compare DNN and VQE, DNN models are always giving the better performance than VQE models. Obviously, when you are using the error mitigation schemes, the results are becoming better. Probably more sophisticated error mitigation schemes might give further better results, but we need to explore them further. And somehow we need to decrease the depth of these circuits. So the previous speaker said that there are ways to actually decrease the number of gates and circuit depths. If we can do so, then probably we can get better results that are in the order of chemical accuracy. Tomography is another thing that we are currently exploring in order to reduce the errors. That's all from my side. Thank you very much for your attention, and I would be happy to take any questions if you have.
Thanks, Chaitanya.
Thanks.
There are already a couple of questions. The first one is they're asking about the optimizer method that you used for your VQE.
So we tried actually multiple optimizers. One of them is LBFGS, another one is like Cobila. So all of them are giving roughly the same results.
Okay.
In the beginning, we find that LBFGS had some problems, specifically for the case of QASM without noise. But once we are dealing with QASM with noise, all of them are roughly the same. So I believe it doesn't matter, but LBFGS will have some problems. Like if you are dealing with Cobila, might be a better option for you to go there.
Okay, and the second question is if you can give an idea about how the DNN is trained to give the VQE parameters.
So this is like very normal classical training. So you have the theta parameters are like the inputs and energies are your outputs. So sorry, the energies and the bond lengths here, sorry. The bond distances are your inputs and energies are the outputs. Sorry, thetas are the outputs here. Distances, for each distance you are trying to get the corresponding theta. That's all it is. And you have one layer here, one or two layers that accordingly you will be doing.
Okay, thanks. Any last question from? Okay, yeah. For the LIH molecule, what is kind of training set do you have, and can you train the parameters with the hardware noise?
So the training again is done on the classical computer. Oh, along with the hardware noise, yeah, we tried also those kind of things. Yes, we definitely did that, and that did not improve at all. Actually, we thought we tried that even for the H2 molecule in the beginning itself, but that did not give us any better results. Like even with hardware noise, when we tried, the results were actually worse. So it's better actually to start with the state vector trained results. I mean, state vector predicted thetas as the initial input rather than hardware predicted thetas.
And I guess that also answered like what kind of trainings are used for the LIH molecule?
Yeah, the same. So LIH molecule training set means like again the distances only. Here also Li and H only two are there. So for each distance we need to predict the thetas. For the case of LIH, the number of thetas that you need to predict will be increasing when compared to the H2. That's the only difference. Apart from that, everything is the same.
Cool, thanks.
Yeah.
And there's one more question. So there's a class for each molecule and the choice of VQC for either 1 or 2 or 4 qubits. Do you have to train the DNN each time?
Yes, that's correct. Because the number of the gates and everything are changing, right? So that's the reason we need to separately train them.
Okay, so which means you will need to generate the training library, that is do the VQE and get the optimized angles for different bond distances.
Yes. Because also the number of thetas could also change, right? Like when you are changing these ones. That's another reason. When you are going to the higher qubits, the number of thetas would be changed when compared to a single qubit, where you have only one theta parameter. That's the reason we need to train separately.
Cool. Okay, so if there are no more questions, I mean, if you have any further questions for Either of the two speakers, you can just continue to post it on the chat, and I request